Let's see your notes. So we're going to start a little bit with your lab. I don't know how far you got, but I want to see. I think we did number 1 altogether, so I can't remember where we stopped and where we didn't get to, so we'll see which one we have and haven't done. We've got a test coming up on the 7th. I told you this chapter has a lot of stuff in it. I am planning on next Monday tutorial being a review tutorial and Wednesday after school being a review time if you would like to come get help. Okay, I will not probably be here next Wednesday during your class, but I will be here after school. It's still up in the air, so I might or might not be. But if I'm not, I'll let you know on Monday before. Okay. All right, so I think we did this first one. Did we do this first one on the lab or no? Get your lab out and let's look and see. It was just last week. That's why we're sort of reviewing, so before we get rolling. We've got lots of stuff to do today. Far things to do. So we need your lab out, we need your notes out, we need your periodic table out, and a calculator. All right, did we do number 1? Did we do A? On your lab, did we do A? Yeah. Okay, so A is done. I'm going to go to the next one, maybe. Did we do G? Okay, let's do G so we can remind our brains of what's going on. So, like I told you last time, this lab is a really good lab to have you practice how to write equations, balance equations, write formulas, determine a solid using your solubility rules, figure out your spectator ions, and write a net ionic equation. If you do each of these in here, you will be ready and prepared for the test. If you don't, and I'm not so sure. We are going to do this lab next time. It takes about 5 minutes to do. It's not a lab we're going to turn in, but I want you to see if your predictions were right. Okay, I want you to see if you got a good prediction. So I'm going to walk you through again the steps that I would do if it were me doing these problems. Up above each of them, I like to write what the ion is. So sodium is at Na+. Phosphate is on the back of your periodic table. It's a PO3-. Lead, the 2 tells me the charge, so Pb 2+. Nitrate, NO3-. So that's the first thing I do, is I look at what things I'm putting together. Now, we're going to be putting together aqueous solutions, so I know everything on the reactant side is aqueous. So as I'm making it, the plus is going to separate them, right? So I'm going to put sodium and phosphate together.
Miss Hal?
Yes?
It's Kayla Byler to the Counseling Center.
Okay.
Hey, thank you.
All right, so then we're going to go like this. Na has a +1, phosphate has a -3. So we need 3 sodiums to balance out that phosphate. So we write Na3PO4, and I know it's going to be AQ because I just told you it's going to all be solutions. But if I didn't know that, sodium is a group 1 metal. And so that's part of the NAG, the G on NAG, for NAGSAG, to help you remember. Plus, lead is a +2, nitrate's a -1, so I now need 2 nitrates to go with the lead. So I get Pb, parentheses, NO3, parentheses 2, and this is also AQ. This is the N of NAG. This is nitrates are soluble. Okay, now we use our double displacement, OI, outsides and insides. So we're going to put our outsides together. Okay, sodium and nitrate. So +1, -1, just smash them together. And this has 2 things in it, so it's extremely soluble. It has a group 1 metal and it has a nitrate. So this is definitely aqueous. Plus, we have the I, insides, lead and phosphate. Now, be careful. Make sure you're always writing the positive first. We have a +2 and a -3. So I've got to go with what the common factor is here, right? Which is 6. So I'm going to need 3 leads to go with 2 phosphates. Since phosphate's a group, I put it in parentheses. Now I go through NAGSAG. Are there any nitrates? No. Are there any acetates? No. Are there any group 1 metals? No. Are there any sulfates? No. Are there any ammonias? No. Are there any group 17 metals or nonmetals? That would be fluorine's group. And there's not. So because there's not, this one is my solid. I bring number 2 is my solid, so I bring it down, Pb3, PO4, 2. Now, I need to go back up to the top, and I need to balance it. Just to speed us up a little bit, I'm going to give you this number as a 6. What else do I need to do? Two in front of the first one, okay. One more. 3 in front of the lead. Okay, and I just did that fast so that we can go on. You can bump up that paper like we've done before and go side to side and get them balanced. That's great. You've got to be able to do that. You've got to be able to balance them. One nice thing is if a polyatomic stays the same from one side to the other, you can treat it like an element. So I can say how many PO4s are on this side, how many PO4s are on this side, because they stayed together. Okay? All right, so the next thing I want to do is I want to write what are my spectator ions. What ions are not used to make the solid or the gas or the liquid? Okay, in my products. Which ones didn't make the solid, the gas, or the liquid? Well, it was what made up NaNO3, right? Because that was the other product, which happens to be sodium and nitrate. So I would down here put Na plus AQ and NO3 minus AQ. Now there would actually be 6 of each, but I don't need to worry about how many of each I have. I just need to state what are my spectator ions. The last part I want to do is I want to make the net ionic equation. So my arrow is always going to point to my solid, liquid, or gas. Here we have a solid, so it's Pb3 parentheses PO4 parentheses 2 as my solid. And on the left-hand side, or my reactant side, I say, okay, what ions made that up? Well, if these 2 are my spectators, then the only 2 left are what else is not circled up there. So lead, Pb2+, but I need 3 of them in the aqueous solution to mix with PO4, 3 minus, but I need 2 of them in the aqueous solution to mix. Now, remember I told you you would also need to be able to do a total ionic. Well, this is a shortcut for the net ionic. The shortcut for the total ionic, I look here and my coefficient is 6. I would just take 6 of each of these and put them on both sides, because there's what cancel out. Okay? So that's another way you can do a total ionic. Okay? All right. So let's do this one. L. Oh, by the way, we need to put this right here where lead nitrate, I think, is a second column. Remember that grid we needed to fill out? It's on the second to last page. Because the last page, by the way, is a blank piece of paper that you can rip off and use to do your balancing equations. But this little grid right here, we should be filling out. So the first one we did last time was AgNO3 and sodium carbonate. We should have got Ag2CO3 for right here. So in that first column, first row, put Ag2CO3. And then this one we just did is in the second column, and it's sodium phosphate, so it's the second one down, second column. And we would write Pb3 parentheses PO4 parentheses 2. Okay, we're going to do one more, and then the rest you'll get to do on your own. See if you can do these. Okay, so the next one, sodium phosphate, we just did that on the other page. So Na plus, PO4, 3 minus. Calcium, second column, 2 plus. Chlorine, 1 away from being a noble gas, minus 1. Okay, so that's the first thing I do. Whenever I have to do an equation, I always write down what ions I have. Now I'm going to put them together into their chemical formulas. So sodium and phosphate are going together. Again, Na is plus 1, phosphate is minus 3. I need 3 sodiums to balance it out, so it will add to equal a 0 overall charge. And sodium is an alkali metal, or metals from group 1, so it's going to be AQ, plus calcium chloride. Calcium plus 2, chlorine minus 1. I need 2 negative chlorines to balance out the calcium. Well, chlorine is group 17. That's part of NAGSAG, so it's AQ also. Yields. Now we're going to do the OI, outside, inside. Could use different color. Do Christmas colors here. Outside, sodium and chlorine, NaCl. Well, you better know that that's soluble, because if you dissolve it, it will dissolve in water, right? But if you don't, it's a group 1 metal, and it's a group 17 metal. So it's both G's on NAGSAG. Plus, we're going to do the insides. Calcium is going to go with phosphate. So, again, we have to look at the 2 and the 3 and say, oh, that's 6, right? So we need calcium, we're going to need 3 to make 6. And phosphate, we're going to need 2 to make 6. And I go through NAGSAG. No nitrate, no acetate, no group 1 metal, no sulfate, no ammonia, and no group 17 metal. So it is a solid. There's going to be some that are not, so don't figure the last one's always solid. Make sure you go through NAGSAG. And then here we're going to say, okay, that's calcium, phosphate. I always like to write that down before I go back and balance it, because then I don't forget. Okay, now we're going to go back and balance. This one also will have a 6 in front of the NaCl. So, if I have 6 in front of the NaCl, what are my other numbers? And I'm giving you a hint real fast so we can balance faster. 2 in front of the Na3, good. And 3 in front of the CaCl2, good. All right, so we've got our solid. By the way, I should have put an S. What are my spectators? Which ones are not involved in making the solid? Na and Cl, right? Those are the ones we didn't use to make the solid. So I write down here Na plus AQ and Cl minus AQ. These are my spectator ions. These are the ones that don't get involved. They're just watching the show. Okay, so then I say, okay, what's my net ionic equation? What makes up my solid, my liquid, or my gas? We happen to have a solid here, calcium phosphate. And I go back and I say, okay, what made it up? Well, the things that I didn't circle for my spectators made up my solid. I had my calcium, 2 plus, and I had 3 of them. Plus I had 2 phosphate ions, 3 minus. These are both AQ. Now, if I wanted to write my net ionic equation, or my total ionic equation, all I would have to do is go back to the main equation and say, oh, there's 6 sodium chloride, so I put 6 Na pluses and 6 Cl minuses on both sides. And then I'd have my total ionic equation. Okay? Excuse me for a minute. All right, going forward then. Now we're going to go on to formula mass. This is where you need your periodic table out in front of your face so you can get these. I'll give you a little bit of time at the end to work on these equations, but let's go now back to your notes. So we're not back in your notes at formula mass. There's a lot of things that are in this chapter. They're not hard, but they put them all together. So whenever I do formula mass, I'm using my periodic table. And I'm looking up how many of each I've got. So this is where we use our calculator, and we're going to use our periodic table. I would look up sodium. Sodium on the periodic table is 22.990. Chlorine is 35.45. I would add those up. Okay, that would be the mass of this, which was 0, 4, 485, right? That's how many grams per mole are in sodium chloride. Okay? Yeah, it should be on your thing, is it not? Oh, we already did this part? Some of it? Okay, so let's skip to, did we do number 5 or did we get lost on it? Okay, we did number 5, we did number 1. What else did we do? Number 2. Okay, so you guys, I'm going to give you 3 minutes. 3, 4, and 6. Quickly, I'm going to have somebody put them up. I'll give you who it is in about 2 minutes. Too much talking, I'm going to die. And this was actually over here, so I can put it back over here. Yeah, yep. And you can take the ones that on the door and put those in the same bag too. And I'm okay if this comes down now. I'm tired of looking at myself. We can put it up another time. So you have lots of room that you can do fun stuff with. Let's see. All right, Jace, why don't you put up number 3? Anthony, let's have you do number 6. McKay, let's have you do number 4. Okay, make sure you're checking these as they get put up. And if you just want to put up the answer, that's great. And then if we all agree, we'll move on.
Is it okay if I did it wrong? Try it.
What did you do wrong?
4. I'm not sure if I did it wrong, but like
4. So you have 1 of those, 2 of these, and 2 of those. That's
I'm
it.
pretty sure that I did it right. But
Okay, put it up. Okay, so look up real here. Number 3, thumbs up that you got that. Thumbs down you didn't. Want to see some thumbs up? Okay, number 4, thumbs up, thumbs down. Thumbs up again. And number 6, thumbs up, thumbs down. Okay, good job. Now, this MOL brings in my little pet peeve. I don't know if you know my pet peeve. They shortened mole by taking the E off, but they did not shorten molecule. So we have to write molecule out, but we get to shorten mole by 1 letter. I'm so excited. No, it's one of my major pet peeves. I don't know who did it, but it drives me nuts. So we're going to go into this next little part. I'm going to have you watch a couple of videos.
Mole is an animal that burrows in the ground.
Or a spot on your chin that you gotta shape around.
But there's another kind of mole that's of interest to me.
That's the kind of mold they use in chemistry.
A mole is a unit
Or have your heart.
containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend.
Say you had a mole paints trivia around the world. Give to each of the 5 alien grown-ups, boys and girls. There wouldn't be a single person down and out of luck, cause everybody in the world will get $1 trillion bucks.
Or say you had a mole of paper stacked up towards the sky. Paper's awful thin, but that pile would get so high it'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. A mole is a unit
Or have your heart.
containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend.
Suppose a mole of marshmallows fell upon the planet over each square inch of land, and see, think that you could stand it? That layer would be 12 miles high, and of course block out our sun. We're talking close to 5 billion trillion tons.
Well, maybe we could save ourselves if we all started eating 1 marshmallow each second, not 2, cause that'd be cheating. With 5 billion people munching, how long do you think it'd take? 40 million years, and that's without a bathroom break. A mole is a unit
Or have your heart.
containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend. Say you had a mole of atoms, the pile would be immense. Should I say the answer now or leave you in suspense?
Well, atoms also very small, you understand. You could hold a mole of atoms in the palm of your hand.
So shake a little sugar in the middle of your palm.
Now you don't want to spill it, so try and stay so calm.
You hardly can imagine
And barely realize
there's more atoms in the sugar.
than stars up in the sky.
A mole is a unit
Or have your heart.
containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend.
Okay, so now we're going to go on to a TED Talk that explains a little bit more about what a mole is. Now that you've got that jive down, right? It's going to stick in your head. Mole is a unit.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so in your notes there is this mole map that I've created for you that will help you to go back and forth between grams and atoms through the mole. This is something maybe I would draw on my card for the test if you don't have it down or don't understand it. We're going to do some problems. I've got the mole map up here at the top so that we can look at each thing as we go. So we're going to be going from one side to the other. The first thing you want to do when you're presented a problem like this is find out, number one, where am I and where am I going? So what is the mass? So I'm trying to get here of this many atoms. I am right here. So I've got to go all the way over. Well, the arrows that go that way are red. So I'm going to follow the red arrows as I go. And since I'm got an atom, just an element, I can just use what's on the periodic table. So I'm going to always start with what they gave me. I'm going to change it to blue. So 3.45 times 10 to the 22nd atoms of Fe. Always start with what I'm given. This first red arrow says I put 1 mole on top. So I put 1 mole of Fe on top. And on the bottom, I put Avogadro's number. We're going to use 6.022 times 10 to the 23rd because that gives us 4 significant figures rather than 3. And we would put atoms, because it's just an element, of Fe. Atoms of Fe would cancel out. We are now in the yellow on the mole. So the next thing over that I want to do is I want to use that red arrow. Well, it says on the bottom I need to put 1 mole of Fe. On the top I put grams. I get the grams from the periodic table. So I look for Fe. It's number 26 on the periodic table. But its mass is 55.485. No, 845. I got it. That makes it 845 grams of Fe. So then my moles of Fe cancel out. How many in here have a TI? 83 or 81 or 85, something like that. Okay, would you put Avogadro's number in for me right now? I'm going to show you a shortcut. So 6.022 times 10 to the 23rd, and then just hit enter. And if I can get batteries for my other ones, I'll get them out and you will use them, and that everybody can have it. Okay, has everybody got that in as enter? Okay, right above your on button, there's an STO, stow. So hit stow, and then hit the green button, which is your alpha button, and right underneath that is the A, so hit that. So it's a math button. I think also it's an A. So alpha A, and then hit enter. Then every time you hit alpha A, it brings up Avogadro's number, and you don't have to keep putting it in. Okay? So if you were to do this problem and you had the TI that we just put the Avogadro's number in, you'd put 3.45 times 10 to the 22nd times 55.845, divide, parentheses, alpha A, close parentheses, inner. You're done. If you didn't have that ability to stow, then you're going to have to put Avogadro's number in each time. Okay? So it's sort of nice to be able to do that. So let's see what we get for an answer over here. We should be labeling it grams of Fe. And we should be giving 1, 2, 3 significant figures. It looks like I've copied that mole map twice, so I'm going to have to make sure I go back to that slide and take one of those mole maps off. They're on top of each other. Slid. Okay, anybody got it? What do we get? Somebody be brave. Three numbers. 3.20. Is that what it rounded to? Thumbs up, I got that. Thumbs down, I didn't. Okay, looks like most of you got it. Good. Okay, now we're going to go backwards. We're now going to use the green arrows, and we're going to go backwards. We're going to start with grams over here, and we're going to end with atoms over here. So, starting again with what we have, 45.23 grams of Ag. So the first thing I'm going to do is I'm going to put 1 mole of Ag on the top, but then I've got to look on the periodic table to find out how many grams of Ag there are. So Ag is number 47 on the periodic table, and its mass is 107.87. So at this point I can cross out grams of Ag. Whatever you have on the top has got to be on the bottom because you've got to cancel them out. The next step, I'm now at moles. I'm not in the center in the yellow. I'm going to the left. So I'm now going to put Avogadro's number on the top. 6.022 times 10 to the 23rd atoms of silver. And on the bottom, 1 mole of silver. At this point, I can cross out moles of silver. And I can put it through my calculator. Just get in the habit of whatever on the bottom, divide, put it in parentheses, and then close the parentheses. If you get in the habit of that, even if you don't need it, it won't hurt to have it. But when you do need it, it won't mess you up. So those of you that put Avogadro's number in, you just go 45.23 times alpha A, divide parentheses 107.87, close parentheses, done. And we have 1, 2, 3, 4 significant figures that were given, so we should report 4 over here. And it should be atoms of Ag. Okay, what do we get to 4 significant figures? .525 times 10 to the 23rd. Awesome. Now, the biggest mistake I see is kids give me this. They forget to look for the exponents. So at the end, you should have a 23, E23 or something like that. It's times 10 to the 23rd. Okay, so make sure you don't forget that. All right, let's go on to the next one. Okay, on this one now, we're looking for the mass. When it says mass, that's grams. You're looking for grams. Okay, so I'm looking to come over here. And I started with molecule, so I'm over here. But molecule is a compound, right? So before I start writing anything down, I need to add up the mass of that compound. So I'm going to come over here, carbon, 12.011. Chlorine, I have 4 of them at 35.45. I've got a lot of these memorized because I use them so much. And you'll have a lot of them memorized because you use them so much, especially oxygen and hydrogen. Okay, so you're going to plug that through. And we're going to get 70, 82, somewhere around 82. Nope, try that again. Plus another 70. So 150. 153.81. Okay, grams per mole. And I'm honoring, I do put the E on because I'm just being, me. Okay, that's grams per mole of CCl4. All right, so now we can go ahead and do the rest of the calculations here. So put in what you know, 4.53 times, that's a point by the way, times 10 to the 24 molecules. Wish they would have shortened that. CCl4. Starting here, following the red arrows back. So 1 mole on the top, CCl4, Avogadro's number on the bottom. That's molecules of CCl4. If I have to write Avogadro's number a lot, you know what I do? I just put up here a circle is equal to 6.022 times 10 to the 23rd, and then I just put a circle in my thing so I know it's Avogadro's number. Okay, because that gets annoying after a while too. Okay, molecules cancel out. Then we go to the next one. We're now moles in the center. We're heading towards grams, so I put 1 mole on the bottom. 1 mole CCl4. And on the top, I've got to put the mass, which we added up, 153.81 grams CCl4. Here, moles go out. Remember, you're going to times through the top, divide parentheses on the bottom. We have 1, 2, 3 significant figures, so we need 3 significant figures in the end. The units are going to be grams of CCl4, or carbon tetrachloride. $1.16. Okay. Do I have a second on that? I got 1,160 grams. Okay. Top one, yes, thumbs up. Bottom one, thumbs up. Okay, it looks like it's the top one. So on this one right here, I'm guessing that it went like this. Did you see that? On yours, the one that gave me 116, 1.116. Did it have an exponent? Okay, watch that because this would have been right if you'd have put times 10 to the third. Once you get to 1,000, you really should be putting it in scientific notation anyway. So that would be more correct. Okay, so now we go to the next one. Okay, again, we are just stopping here at moles though. We are stopping at moles. We are trying to get here. But we are right here right now. Since we have to have grams to get from grams to moles, I'm going to have to add up that iron nitrate, iron 2 nitrate. So Fe 55.845, nitrate, we have 2 of them, 14.007, and oxygen, 3 times 2 is 6, so we have 15.999. Add that up. $179.85. Okay, and that's grams per mole of iron 2 nitrate. Okay, again, start with what you're given. So I'm starting with 36.47 grams of FeNO3, 2. This time I'm only going to have one conversion because I'm only going from grams to moles. I'm stopping there. So on the top I'm going to put 1 mole of FeNO3, 2. And on the bottom, I'm going to put the 179.85 grams of FeNO3, 2. Now, another little shortcut that I like to do when I've added this up and it's in my calculator, I set my thing up, but I leave this on because if I only have one step, I'm either timesing or I'm dividing by it, right? So if I've added this up, all I have to do is hit the 1 over x button and times it by this, and I'm done. Okay? So it saves a step. Either way, we're going to take 36.47 divided by 179.85. We're going to end up with a decimal, so 0 point something, and we have 4 significant figures. So mole, FeNO3, 2. What is our numbers? 2028? Awesome. Everybody's head was nodding, so I took that as a head nod. So not hard, you just need to know what to put where. And if you have the mole map down, it tells you where to put what where, right? So hopefully this is not too difficult. If you're having problems, you need to come probably see me. Okay, so this one, I want you to do this one, but I want you to use, because this is the same one because I did a copy paste, let's do 8.01 grams there. Now let's make it funner. 88, what? You don't have any room, it just are cut off? Okay, so let's just do that top one. I want you to see if you can do the top one by yourself then. So there's no room for the bottom one. We'll just sort of X it out anyway because it was just a copy and paste. So see if you can set that top one up by yourself. How do we do? We do okay? Thumbs up, I got this. Thumbs down, I don't. Thumbs sideways, I'm getting there. I saw some thumbs. One more time. Thumbs up, I'm getting this. Thumbs down, I'm not. Thumbs sideways, I'm on my way. Okay, all right. So if you're struggling with that, come see me. We're now stepping up. Now we're going to put together what we just learned with what we've been doing before. Okay, so this is called stoichiometry. You want to get somebody, say, I know stoichiometry, and they'll look, you're like you're weird, but that's okay. Stoichiometry is a way that it's basically like a recipe. Okay, if I want to make so many cookies and I don't want any extras, how much of each thing do I need? So here we need to calculate the mass of aluminum. So I'm trying to find the grams. Anytime it says mass, I'm looking for grams of aluminum that must be used to produce 500 points. So that means I have 3 significant figures of aluminum oxide. And they gave me an equation, but it's not balanced. So the first thing I need to do is balance the equation. Because in order to do stoichiometry, I have to have a balanced equation. So what do I need to balance this equation? 4, 3, 2. Sounds like you're counting down. 1, blast off. Okay, we do need that. Now, we're always going to start with what we have. The key here is these numbers right here, those are how many moles. That's a mole ratio. So we have to get our grams into moles before we can use the equation to trade from one thing to another. So we're going to start with our 500 grams, and it's 500 dot, which means 3 significant figures, grams of aluminum oxide. Well, in order to get from grams of aluminum oxide to moles, I've got to add up how much is 1 mole. So aluminum 2 times 26.98. I can't see that last one. Is it a 2? Can't read it. Okay, I'll take your word for it. And then oxygen, we have 3 times 15.999. Notice I did not use the coefficient in this part. I'm just adding up the mass of the chemical compound. Okay, just the mass of the chemical compound. So somebody do that real quick for me. I'm going to keep doing our mole here, Al2O3 in grams of Al2O3. .961. Okay, and that's grams per mole. So we put 101.96. Okay, at that point I can cancel out grams, right? This is where my mole ratio comes from. I have moles of something, but I want to find out how much I've got of something else. Once I'm in moles, I can go to the equation and say, oh, okay, well, I'm going from this one to this one. So I'm going to put the 2 moles of aluminum oxide on the bottom, and I'm going to put the 4 moles of aluminum on top. That allows me, that equation allows me to go from moles of one thing to moles of something new. Okay? Then we go back and we've got to change the moles back into grams, but it's of something new. So on the bottom I would put 1 mole of aluminum, and on the top I would put that 26.982 grams of aluminum. Here, moles of aluminum cancel, and I can now figure out how many grams of aluminum I needed to start with. Remember, as we're putting this through, divide parentheses times through the bottom and then close parentheses. If you don't, you're going to end up with the wrong answer. So we should have 3 significant figures in our end answer. Somebody got the answer? 265? Do you have a second on that? Okay. Good? All right. Questions with this? We're going to add a little bit more. Actually, I think we do one more of these. Can't remember. Okay, going on to the next one. Okay, so now we got to talk about limiting reagent and excess reagent. If I'm in industry and I'm trying to make ammonia, then I've got to put nitrogen and hydrogen together. I don't want to put more chemical together than is going to make my product. I don't want to waste chemical. Because if I waste chemical, that's like throwing money down the drain. So I want to know which one is going to run out first. Which one do I need to have in excess? Can I have a lot of excess, or can I get away with just a little excess? So when I say limiting reaction, or limiting reagent, that's what you're going to run out of. And these are always reactants. If I have to say excess reagent, it's still my reactant, but it's what I have too much of. Okay? So, if you're thinking about it like hot dogs, you go to buy the store and you got 5 hot dogs, but you only get 4 buns. Well, I can only make 4 hot dogs with buns. I have 1 extra hot dog. That's a simple one. If you go more complex, like you're making a hamburger, you have a lot of things that are your reactants to get to your products. So you have one thing that is limiting. That happens to be the hamburger patty. I can only make 3 hamburgers because I only have 3 hamburger patties. But I have in excess 3 things of cheese, 1 tomato, and 1 bun. Okay, so I have more things in excess. Did you have a question? Yeah. Just push this little button in.
Oh, interesting.
Okay. All right, so let's go on and see if we can figure this out. Here we have an equation. So we have given to us 4 grams of methane. This is what I do when I have a problem like this. I write the equation out, and either above or below, I put what they gave me. I have 4 grams of methane, and I have 15 grams of chlorine. So I don't get them screwed up. They want to know what's the limiting. Okay, well, I've got to have a balanced equation. This is not a balanced equation, so I'm going to have to balance it first. So what do I need to do to balance this equation? Do your hydrogens first on this one. That's sort of backwards, but do your hydrogens first on this one. So if I do my hydrogens first, this becomes a 4, right? That means I have 4 plus 4 chlorines. I need 8 on this side, so I put a 4 here, and everybody's happy. Okay, now, the next thing that I need to do, though, is I need to figure out the mass of each of these individual ones. So I'm going to take a carbon, 12.011. I'm going to take 4 hydrogens, 1.008 times 4. I'm going to add that up. I'm going to do the same thing here with chlorine. I just have to times chlorine by 2. So 2 times 35.45 and get an answer. So let's do that. You just sort of have to hit it. Don't do it slow. Yeah, just hit it. Bam it. So you just put it up here where you want it. Just hit it. Yeah, act like you're angry. Okay, what did we get for this one? It was 16 something, wasn't it? 0.42 grams per mole. 0.43? Okay, and when this one was 70 point something, 0.90 grams per mole. Okay, so we've got the masses now. All we have to do is bring down this 4, go 4.00 grams divided by this, and it'll give me moles. And I go 15.0 grams divided by the 70, and that will give me moles. So let's do this one. We'll end up with 0.249. Okay, because we had 3 significant figures. We'll take 3. That's how many moles of CH4. Okay, what about this one? 0. I think that one's also a 2, isn't it? 211. Is it 211? 212. 212 moles of Cl2. Well, they look pretty close to each other, but the key is this ratio. For every one of these, I need 4 of these. For every one methane, do I have 4 chlorines? For every one methane, do I have 4 chlorines? It's like, it's sort of like methane's like a quarter, because that would be like 0.25, right? If I times that by 4, that would be $1. Do I have $1 here? No. So this is going to be my excess. I have too much of it for what I have here. So this right here, so chlorine is my limiting, the one I'm going to run out of. I don't have enough. That means CH4 is my excess. Okay, I can do that by just looking. Now, there's sometimes they get really close, like it's a 3 to 4 ratio. And if it's a 3 to 4 ratio, you've got to pick one of these moles and change it into moles of the other by using the ratio. Okay, but when it's 1 to 4, I should be able to tell, do I have 4 times as much or not? Okay, so now we go and say, what is the maximum mass of carbon tetrachloride that can be made? So this is theoretical, because we know in lab and in real life, when we go to make something, sometimes you lose some stuff to the floor, like I might have lost a hamburger bun to the floor. I'm not going to make a hamburger with that. Or I might have lost a patty to the floor, so that reduces how much I can make. So we're going to use our limiting reactant, so we're going to use what we're going to run out of, and we're going to go to carbon tetrachloride. Okay? So we're saving ourselves a step as long as we write these down in between. So 0.212 moles Cl2. Now I'm going to use the ratio. I'm going to use this number up here, this 4 and this 1. So I'm going to put 4 moles Cl2 on the bottom and 1 mole carbon tetrachloride on top. But we need to figure out how much is in carbon tetrachloride. So over here, carbon 12.011, chlorine, I have 4 of them at 35.45. Thought we already added this up. Did we already add this up? That sounds really familiar. Maybe it's just another class. So we're going to add that up to get the mass. So over here, we're going to put 1 mole CCl4 and the mass of CCl4 on the top. Moles cancel out here. So what do we get over here? Say it real loud. Okay, grams per mole. So 153.81, and then we can cross out moles. And basically on this one, we will have the number 4 on the bottom. So we just take 0.212 times 153.81 divided by 4, and we can get our answer of grams of CCl4, the maximum we could make. And we're going to have 3 significant figures. What? 8.15. Do I have a thumbs up or a second? Okay. Now, this is the part that gets a little tricky and throws a lot of kids off. We have excess, but we want to know how much excess. As a person that's trying to make money, I don't want to throw this money away. So I want to find out how much was excess and how much I could have taken away and not put in with that to make it. Okay? So we're going to again take the 2.12, because we're always going to start with our limiting, because that's what we're going to be using all up, of Cl2 this time. But this time I'm going to go from chlorine to methane. Okay? So I'm going to use that ratio. So I'm going to use the 4 moles of chlorine on the bottom and 1 mole of methane on the top. Moles of chlorine will go out. And then since I already added methane up, right? I already added methane up. I can just put 1 mole of methane on the bottom. That didn't write very good at the bottom, sorry. 16.043 grams of methane on the top. And I can times that through. So I'm going to go 0.212 times 16 divided by 4. That will tell me how much I used. Not how much is left over, but how much did I use. So let's put an answer here of how much I used. And we need 3 significant figures. 0.850. Okay, that's how much I used. Well, I had 4 grams, right? So if I take 4 grams minus 0.850, then I'm going to end up with 3.15 grams in excess, right? Did I do that math right? So I could have done the reaction almost another 4 times with what was left over. Okay? How do we feel? Okay, I want to stop right here because it's been a lot of new stuff today, and I want to give you time to work on your precipitation reactions or to work on your... By the way, how many finished their Learn Smarts like they were supposed to? 1, 2, 3, 4. Learn Smarts need to be done. Okay, I told you they need to be done by today. Today, you should be starting on your homeworks. Okay, so we really need to get going on those if you haven't, okay? Remember that all the Learn Smarts and the homeworks and the labs can be well, I don't know if they can be redone. You can do them if you haven't done them. The labs can be redone if you don't like your score on them. Just upload them and I'll get them graded. Okay, you have until January 10th on that. All right, so the rest of you, work on this. Get a buddy, check it with a buddy, make sure you're working and doing what you need to get done. Okay? If you need help, I'm around. Did it stick on you?